Welcome all. Welcome, it's good that you're all here, because passwords are going to disappear. I think in 5 years' time, none of us are using passwords anymore. You're all going to switch to passkeys. So what you're going to learn today, why are passwords so bad? Many of you might know already, but I'll tell it again, and why passkeys are great. Passkeys are going to solve a lot of the problems that we have with passwords at the moment. I will also tell what passkeys are and how they work. And I will tell how to test for vulnerabilities in passwords. How can we pentest passkeys? And we actually did pentest passkeys. So I will also tell a bit about the real-world vulnerabilities that we found in passkeys. And of course, we did a responsible disclosure on them on some implementations. This is all based, everything I'm going to tell today is based on the research of my master's student, Peizhou Chen. He did his master's research from the University of Twente at Pentesting, which is my employer. I supervised him, and we really found great results. So I hope you're interested in what I'm going to tell today. So again, passwords are basically very simple. How many of you guys already used passwords? Maybe fingers? Passkeys, sorry, passkeys. How many people did? Almost everyone. No, that's not true. About half of you already use passkeys. So those of you who use them know they're actually very simple. So how does it work? You want to log in to an application, in this case to Google. You enter your username. The application asks you, please provide your passkey, and you do that typically by providing biometrics. So by using Face ID, by using Touch ID, by providing a fingerprint, or in some cases, by entering a PIN code. That's the only thing you need to do. And show your face, enter a PIN code, touch your device. Your device is authenticating for you, and you're logged in. Much easier than typing in a password, right? So this is actually how you authenticate. Of course, you also need to register a passkey with an application, but that's just as simple. What you're doing is create a passkey, again click on create a passkey, authenticate by means of your face or your finger or your PIN code, and your device authenticates you. Very easy. On the other hand, passwords are really bad. When people start hacking, they think most companies get hacked by things like SQL injection of cross-site scripting or whatever. I can tell you I've been working at Computest as a pen tester for 10 years, also saw quite some incidents. I don't remember ever having seen anyone that's got hacked by a cross-site scripting attack. I'm sorry, guys. I did see loads and loads of companies that got compromised due to weak passwords. So what happens is basically two things. Either attackers just guess a password, for example, because a password got stolen. I think this is the last number. This is the amount of passwords that got stolen. That's 14 billion already. Or people fall for phishing attacks. You all know what a phishing attack is. An attacker presents a malicious website, but makes it seem like that's the right website, tricks users to enter their password. Oh, and then the attacker has the user's passwords. A lot of real-world attacks. I would even say perhaps most of real-world attacks are occurring because those one, two things. Passwords are really the main security risk we have at the moment. We don't want that anymore. So to reiterate, passwords are not user-friendly. You need to remember them. You need to type them in. Ideally, you remember a different password for every website. Nobody's going to do that. While on the other hand, passkeys are just simple gestures. Passwords are vulnerable to phishing. You can easily type in a password on a website that's not the right one. Passkeys on the other end are scoped. They're technically set up in such a way that they're only going to work for the one website that they're intended for. Passwords are also vulnerable to password guessing. On the other hand, passkeys are a private key that cannot be exported or guessed. And passwords are a single factor, only something you know. While passkeys on the other end are by design multi-factor. They're always something you have, which is the device that you use to authenticate, plus either something you are, biometrics, or something you know, a PIN code. Who's actually using passwords? Sorry, who's actually using passkeys? There's questions already. Oh, no, sorry, it was not a question for the. It was not a question for the room. It was a question for which companies are using passkeys, and basically all the big companies allow the use of passkeys. We also see that sipping down to the smaller companies nowadays. So at my company at Computest, we are also helping already quite a lot of the medium-sized companies in the Netherlands implementing passkeys in a secure way. And we are slowly also going to see that the smaller companies are implementing passkeys as well. And like I said, in 5 years' time, I think passkeys is all that we have. So maybe good to state the roles that we have in passkeys. So there's basically the user and 3 important roles. We have the authenticator, which in the example was my phone. We have the client, which was my browser. And we have the relying party, which is Google. We were trying to log in to Google. So basically, passkeys consist of 2 protocols. Communication between the authenticator and the client. That part has been called CTAP2. So that basically tells how a browser should communicate with the device. Today I'm not going to talk much about that. It's not so interesting for us now. And the other part is about how clients talk with relying parties. So that's basically a browser API that's offered that relying parties can talk to. It's called Webauthn. And when the big companies were going to implement this, the very first thing they did is, we're not going to call this FIDO2, we're not going to call this CTAP2, because nobody is going to use that or remember that. So the first thing they did was, we're going to rebrand this all to passkeys. But just remember, passkeys is just the marketing name for FIDO2. So how does the protocol work? We have Google and we have my browser. From Google, first, of course, Google at the moment that we want to register already knows our username because we told that. And the relying party, Google in this case, is sending the user ID to the client. Then the client, the browser, or the device is creating a key pair, a public-private key pair, and then a credential ID and a public key is sent back to Google. For the authentication, we have a relying party. Again, knows already who's going to authenticate, so it sends the credential ID to that user and a challenge to the client. So remember, the client is the browser. Then the browser creates a signature, which is a challenge signed with a private key. And that private key and challenge is sent back to the relying party. But is it secure? And I can tell you, I guess the pass key protocol itself is secure. I haven't seen any issues with the protocol itself. But the security, of course, depends on how people implement this protocol. And an insecure implementation might lead to account takeover. If a relying party implements the protocol wrong, then we can do nasty stuff, take over an account. So what we want to do, we want to test if the relying parties implemented this well, if they're secure. That's what we're pen testers for, right? Sure. I need the microphones for that. Sorry, the music outside is quite loud.
Yeah? Oh, it's on. Yeah. Why can't you do a man in the middle on this protocol?
Yeah, very good. One of the things I'm going to mention. So, earlier pen testing approaches, what they looked like was an attack. Good to know is we talked about the relying party as basically one thing, but secretly the relying party in this protocol is 2 things. It's the part of the relying party that lives in the browser, basically the client-side application of the relying party, the client's part of Google, and it's a server that's controlled by the relying party. And nobody actually talks about this, but this is important. Because what previous approaches did was they basically faked this entire part. They just sent fake messages to the browser application of the relying party, which is a nice approach. But the problem is, and we all know this from pen testing, the problem is that we cannot distinguish between client and server-side prevention. We can test this, and maybe we see that this attack doesn't work, but we don't know if the protection is in the browser part or if the prevention is in the server part. And to prevent that, we implemented a different approach using our favorite pen testing tool, Burp Suite. We implemented a Burp Suite extension that tries to intercept this arrow and tries to modify traffic in there. Sounds easy, right? No, not easy. Reason for that is that, interesting enough, this is totally unspecified. In the protocol, it nowhere says how the relying party actually should get its data to the backend. Of course, we can guess it needs somehow to get the signature to the backend because the signature needs to be verified. But it doesn't say how to be done, how that should be done. And of course, if it's not specified, everyone is going to do it in their own way. So some people wrap it in base 64, some people double wrap it in base 64. I have no idea why they do that, but they do it. It's not insecure, but it makes it a headache for us. It also means that for every relying party, we had to do some custom coding in our Burp extension. So unfortunately, we don't have a one-size-fits-all extension, but for every extension, we need to mess around with code in our extension. But that's just the way it works. It's not specified how this traffic should be done. So we looked at 10 potential implementation difficulties, problems in Webauthn. These 10, and I'm going to through all of these 10, and I'm also going to tell at the end if they are typically implemented well or not. First one, fake signatures. We can just try to fake the signature, put a total nonsense signature, and hope our message gets accepted anyway. I saw an earlier talk today also where they just didn't take the signature at all. This is an attack vector that really works quite often in real life. People quite often just escape this signature check because it's a pain. Of course, if the signature is not checked by the relying party, then we can just pretend who we are. We can just sign everything and we can try to be any user. So if they don't check the signature, you have immediate account takeover. Second vulnerability is responding to the wrong challenge. So remember, the client needs to respond with a signed signature. We can just try to forward a totally different challenge and see if it still gets accepted. If that's the case, then the application is vulnerable to all kinds of relay attacks. Maybe you can bypass user content. Probably it opens the door to cross-site request forgery. So relying parties really need to check that the signature matches the signature sent before. Another nice one is replaying the same challenge. So we actually did find one relying party where we could replay the same challenge multiple times. It allowed us also to create multiple devices, register multiple devices based on the same challenge. We were actually not quite sure if this was a problem. At first we thought probably this is not a problem. Then we started Googling around a bit, and we found an earlier CVE that has exactly this problem. So we thought, apparently someone got a CVE for it, so I guess it's a security vulnerability, even though we're still not quite secure of the impact. Another vulnerability is forwarding a message for another relying party. So I lied a bit about the first side of the protocol, because this was a very simplified version. I'm going to expand on the protocol, add details to explain more types of vulnerabilities, and I'll end with the full implementation in the end. Anyway, another part in the protocol is that every message contains the relying party ID, so the ID of the party where we want to log in. Relying party ID within Webauthn is actually very simple. That's just the origin. So if you're trying to authenticate to google.com, your relying party ID is going to be account.google.com. So that message is included in all the messages. It's also included in the signature at the end. So, of course, what you're going to do is try if you can change that origin. Because if you can change the origin, since someone sent a message that's not intended for that party, then we can set up a malicious relying party and forward the messages that we receive to the real relying party. If that's the case, then relying parties can impersonate each other. And that's a nice thing. Actually, we also find the case where we could do that. But then we realized, oops, this attack doesn't work. It doesn't work in practice. And the reason is that the authenticator or the browser also checks that the relying party ID is right. So this is checked on two sides, both on the side of the relying party and on the sides within the browser. So now we can say, okay, it's not so important that the relying party checks this because it's already checked in the browser. And I'm a bit afraid that browsers are going to say it's not so important that we check it because this is already in the relying party. If you find a combination of a misbehaving relying party and a misbehaving browser, you're going to have a very nice attack. We didn't find any misbehaving browsers, but we also didn't look at it. Another thing that's implemented in passkeys is user presence and user verification. These are flags that are included in the protocol. User presence means that the user is physically present. For example, because the user touches a sensor. User verification means that the user is verified, for example, because the user controls the private key, for example, by showing that because of a PIN or a fingerprint or whatever. User presence is required in the protocol. User verification is optional. So if you want, you can say we don't need user verification. So let's have a look how that works in practice. So we're going to try to log into this application. We log in with a passkey. We need to enter the PIN key of our device, of our authenticator. It's not accepted because we entered the wrong PIN. What we're going to do is we are going to mess around with the JavaScript a bit. We're going to add a breakpoint to the place in the JavaScript where this is called. We say user verification we set to false, so it's to discourage. It doesn't require user verification. Let's see if we can now log in without passkey. Sorry, without the PIN code. Yes, now we're logging in to the relying party without us having to provide our PIN codes. So basically the conclusion of the story is if a relying party doesn't check if this user verification flag is actually true, then the entire two-factor step is skipped. Something else that's implemented in passkeys in Webauthn is a signature counter. That signature counter is there to prevent someone from cloning an authenticator. Every time an authenticator signs something, it's increased by 1. So what we tried is what happens if we just send 0. I was expecting we would be rejected. We also tried making a very big jump suddenly to 999. Just curious if we're getting accepted as well or not. And the last 3 issues we have is, last 3 things we checked for is swapping client data type, so basically swapping authentication and registration. Invalidating public key ID, so try an insecure public key algorithm. There is a public key that specifies the algorithm we use. And sending a fake credential ID, so authenticate with a credential that's not registered at all. So we implemented these 10 vulnerabilities in our browser extension. And we ran them against quite some nice real-world Webauthn implementations. So the first 2 are 2 demo applications, webauthn.io and webauthn.settercode.com. And we also did it against 2 relying parties from the real world. Unfortunately, I'm not able to mention their names because we didn't fully verify whether they actually fully fixed everything that we reported to them. But they're both very big real-world applications. I think they have both more than 100 million of users. So, what are the results? Client data type is checked by everyone. Responding to a wrong challenge, nobody falls for that. Forwarding message for another relying party, that's actually not checked by one of the RPs that we checked, so one of the relying parties that we checked. User presence, remember that's required. Also not everyone checks them. User verification is also not required by everyone. Remember that one was optional, so it can be a deliberate choice not to require user verification. And for authentication, we basically see the same. Also, forwarding a message for another relying party is allowed. Forwarding message for another subdomain is allowed for one RP. User presence is not always checked. User verification is not checked by everyone. One party falls actually for the signature counter one. Signature counter 999 is accepted by everyone. It's also not required that you don't allow big jumps, so that's not necessarily a problem. And again, like in the CVE, we found one relying party where we could replay the same challenge. So, of course, we did a nice responsible disclosure. We contacted all those companies where we found vulnerabilities. And I was surprised that actually all responded quite happy. I heard so much horror stories in the past about companies that are very unwilling to fix things or even acknowledge vulnerabilities, but everyone was actually very happy. So setter code, we mentioned the user presence bug. They said, yeah, you're right, and they fixed it straight away. Then relying party number 3, we reported the user presence bug. So remember they didn't check for user presence. They said, yeah, you guys are right, we're going to fix it. And they gave us a nice bounty. And then we had the replay same challenge bug. Remember, this was the thing of which we didn't quite know if there was an impact or not. So they said, we analyzed it, and we think this is not a vulnerability. But we're going to give you a bounty anyway. And that surprised us quite a lot. I never saw that before, that we reported something that was not a vulnerability, but that still gives us a bounty, but we didn't complain. So I think they found it also quite interesting, and they were also a bit confused. And relying party number 4, the user verification bug was confirmed. They confirmed that. And forwarding a message to another RP, they also confirmed that, and they said they're going to fix both. Like I said, I didn't fully verify if everything was fixed or not. So that's the results we had in the real world applications. So for those who are not bored yet, I'm going to go a little bit more deep into the technical details of the protocol yet. This is not needed to understand the main results that we found, but maybe you guys are interested. So like I said, the JavaScript API offers possibilities to create a public key, to register one, or to authenticate. In Webauthn, these are called ceremonies, by the way. You have a registration ceremony and an authentication ceremony. But basically, Webauthn is nothing more than two JavaScript APIs and endpoints. So, of course, we need to send some data to these endpoints. For registration, we send the following parameter. And it is probably hard to read, but it's a lot of details. Basically, what I call is you send a variable that's called public key. And this has all the information that I just showed. So you can see here, there is the ID in there. Remember, that's just the origin. There is the user ID. This is just the base 64 encrypted string of the username. There's this challenge, that's just a random string. The rest is not super important. So we send this, we want to register this username with this challenge, and we get a registration back from the endpoint. So again, there's the ID of the key. There's an attestation object, which I'm going to talk later about, but remember that. There's a client data JSON object I will also talk about. There's authenticator data I will also talk about. And there's the public key that we've just received. That's the public key belonging to the key pair. So this, just to summarize or to give a look ahead, this attestation object is some information we get from the authenticator, the same for authenticator data, and client data JSON is some information about the browser, but I'll get into that in the next slides. So this is about registration. Authentication looks very similar. So again, we are calling the authentication endpoint. We're calling that as a relying party. We are sending the challenge to that authentication endpoint. We include the ID of the public key, because we already know the ID of the user, of the key of the user. And we get a response back, basically a signature. That is a signature over authenticator data and client data JSON. Again, that's the data from the authenticator and the data from the browser. So that's basically a hash over that data. And I didn't tell you what the client data JSON is. This is basically the information that contains the challenge again, and that contains the origin. So this is an object that's created by the browser. And the attestation object. And the attestation object, like I said, this comes from the authenticator. It's a bit nasty format. It's not JSON. It's some CBOR. And it's a CBOR object, which is basically a binary object that contains, it contains all the information I promised you before that would be in it. So the ID of the relying party is in there. There's flags like user verification and user presence is in there. The counter is in there. The credential ID is in there. So that's it. That's the full description of the protocol. So, yeah, what are the lessons that we learned? What did we learn from this? What did we learn from this research? Of course, passwords are bad. You already know it, but I hope for those who don't know that, I convinced you. Passkeys are great. They're going to fully replace passwords, I think, in the near future. But implementing them is very tricky, especially implementing relying parties. There's a lot of things you need to take into account. So if you think, I want passkeys on my website, please don't implement this yourself. Please use an existing library. Or don't, but then you're going to have a lot of fun. And the other thing we learned, pentesting passkeys is fun if you have the right tooling. So thanks again to my student Peizhou Chen, who carried out most of the work here in this presentation. If you would like to read his thesis, it's called Vulnerability Testing for Webauthn. You'll be able to find it if you search for that. If you would like to fiddle around with our tooling, please download it here at this GitHub. Like I said, don't expect a click and ready burp extension for which you only need to press play. It's quite a lot of fiddling around, but if you find it fun to build on that, please feel free to have a look at it. So that's what I wanted to share with you today. Thank you for your attention.
Thank you. Thank you. Sorry for the mic. If you have questions, there's a mic where you can go to and ask your questions. Anything from the internet? No.
Your mic is not on, I think.
Hello? Yeah. You say passwords are bad, passkeys are great. But let's say I store my passkeys in the password manager, as well as randomized passwords. Will it make a difference then still?
I think the difference will be very small. You're going to do that, but all the other millions of the users of the application probably are not going to do that. Yeah. But of course, if you're using randomized passwords in a password manager, then I think you solve most of the problems, because the password manager also makes sure that you're using the right scope. If you're using randomized keys, then you also do what Webauthn is doing. Yeah, so that's just basically a complicated way of implementing passkeys yourself. That's fine. Yeah, sure.
Any more questions? Don't be shy. Still there. There you go.
Excuse me, we have a question from the internet. First time today. From all the available passkeys, like Nitro key, One key, and YubiKey, or anything else, which one would you advise?
Where is the person asking the question?
It's from the internet.
Yeah, from the internet. I couldn't hear it very well. Would you be able to repeat it once more? Maybe the volume can be slightly up as well.
Yeah. From all the available passkeys, for example, Nitro key, One key, and YubiKey, or something else, which one would you advise people using?
Yeah, that's a very good question. So basically, you're saying what authenticator is the best one? That's a good question. Of course, as far as our research goes, we have mainly looked at the Webauthn part of the protocol. So we have mainly looked at the side on which the authenticators implement, how the relying party is implemented. So I don't know too much about the authenticator side of things. An important distinction that you see is there's physical keys, like a separate device that you plug in your laptop. And nowadays you can also just use a laptop with biometrics to log in. I guess it depends, but like I said, I'm not an expert in this, but I guess it mainly depends on what you're most afraid of being stolen. Are you afraid of having your laptop stolen, or are you afraid of having your YubiKey stolen? In any case, I think it is good that you use an authenticator that has some form of biometrics. I think biometrics are generally easier to use, maybe even stronger than just purely PIN codes. So I hope that answers your question. I'm not familiar with all the differences between the different vendors.
Another question from the microphone.
So in one of your slides, one of the input mentioned something about cross-origin.
Mm-hmm.
And I looked at that and went, that's probably a minefield.
Yes, if I remember correctly, of course it's a very long RFC, so I don't remember all parts of the RFC by head, but if I remember correctly, this has something to do with an iframe that's in a different origin than the iframe in which you're loading it in. So this is not something like cross-origin authentication or anything like that. This has to do with iframes within with multiple origins. I'm saying that by heart, so I would need to check in the RFC.
Thank you. Nice talk.
And another one.
So hello. So I'm maintaining a password manager, and when we looked at implementing passkeys in software, we noticed there is a certification for the authenticator. Did you test if the relying parties are enforcing?
I'm sorry, the music is very loud. Can you talk a little bit closer to the microphone?
Yeah.
That's much better.
Did you notice if any of the relying parties are enforcing the certification field or not? Because some authenticator can have a certification, and open source ones, for example, cannot really. Or do they all ignore the certification?
You mean the verification part?
The certification, like hardware certifications and stuff like that.
Yeah, you're talking about the certification of the authenticator itself, right? Yeah, exactly. I didn't mention this, and indeed the fact that I didn't mention this, also the reason is indeed not used too much. So there is, in the protocol, there's an option that you say that you only allow certain certified authenticators for your application. I've seen nobody that's using that.
Any more questions? So, thank you, Matthijs.
All right, thank you.